Okay, so here's what we've got today. So we're going to kind of briefly touch base on where we're at with writing chemical formulas. And then we've got this big lab to do on on conductivity. So now that we kind of know how to write chemical formulas, now we're going to kind of put that to use. So a couple of things on that assignment that I gave back. When you have like these polyatomic ions, so let's say you're going to have, I don't know, say you're going to have aluminum acetate, okay? So for now, like on the lab, I'm just going to give you the names of the formulas, okay? You're to the point now that where you've got to be able to write those formulas. So there's a couple of things you can do. If you want to think of this as old school, first off, the first thing you've got to be able to do, no matter how you think it through, you've got to be able to figure out what the charge is on these elements, okay? If you can't, the cation and the anion, if you can't do that, you're just dead in the water. So you've got to have out that periodic table with like the boxes up there at the top that says, okay, hey, here are the most common ones. So go in there, you find aluminum. It has a charge of 3+, okay? Now, why don't we put, because it's 3+, why don't we put aluminum 3 acetate? Why do we not need to put that Roman numeral 3 on the end of it? Mr. Grow.
There's only aluminum with a charge of 3.
Fantastic. Aluminum is only going to form an ion with a charge of 3+, okay? That's it. There's no variation to this. Those 3 valence electrons, it's going to get rid of them. It wants to look like neon. This is why we're not going to put that Roman numeral 3. It is not one that has like multiple personalities. Boom, this is it. It's Al3+. That's it, nothing else. Now, you got acetate, which is this big molecular compound, CH2H3O2 with a charge of 1-, okay? So, at the end of the day, here's the deal. And I don't care how you think through this. If you like electron dots, and you go, oh, here's aluminum, and it has 3 dots. It wants to get rid of 3 electrons. Whether it's acetate, whether it's chloride, anything that has a charge of 1-, that can only take in 1 of those electrons, which means I've got to have 3 of those to take that in. So if you like that idea of Lewis dots, okay, hey, I got 3 valence electrons. Acetate can only take in 1 of them. I got to have 3 of those to complete that puzzle. So if you like that visual idea, go with that, okay? If you like the visual idea of that big square, oh, here's a big square, that's going to have a charge of 3+. Acetate's going to be a smaller one, which means I've got to have 3 of those to complete that square. So if you like that visual approach, that's cool, okay? The other thing that you can do, and this is actually the most efficient, is realize that no matter what, how you end up with Lewis dots, whether you do the visual with the pieces, but no matter what, your guiding light is always the idea that the sum of all the oxidation numbers have to add up to equal to 0, because that's the most stable configuration, okay? So if you keep that in mind, it's like, no matter what happens, I don't care how you get there. I don't care which side of the mountain you climb up to. But you got to get to the top of the mountain that says, when I write that chemical formula, everything has to add up to equal to 0. Now, notice I'm not saying the oxidation numbers are 0, okay? The sum of the oxidation numbers have to be equal to 0. Now, here's the other thing. Acetate is C2H3O2. That is sacred. Okay, you cannot change the formula of the C2H3O2. That's what makes it acetate. If you change that and make that C2H3O, then it's no longer acetate. So when you have these polyatomic ions, those are sacred. They cannot be touched. They cannot be altered. Okay, it's a rule. You can't touch them. So what is the most efficient is kind of like this cross step. You write these out with their oxidation numbers. Al3+, acetate 1-. You take that value of 1 and you bring that down here, that's gonna be the subscript for the aluminum. You take that 3 and you move it down here, that's gonna be the subscript for the acetate, okay? You just cross these over. So that means you're gonna end up with Al, and now I'm gonna do this wrong, okay? I'm going to do this wrong. Do not do what I'm going to do. Do not do this, okay? Oh, I need 3 of those, so I'm gonna go, C2H3O, and then I need 3 of those, so I'll put a 3 there. So why is that a train wreck for any number of reasons? Parker, what's one reason that's a train wreck?
The oxygen needs a 2 after it, not a 3,
Why?
because acetate has 2 oxygens.
Okay? So as soon as I put that 3 there, it is no longer acetate. Okay? It is no longer the acetate polyatomic ion. Okay? We've changed it into something else. So that's why I said, when you have these big polyatomic ions, those are absolutely sacred. Okay? So I've got to have a 2 out here. So I'll just put a 3 out there. Ella, why is that going to be a train wreck?
It says 23.
Yeah, if I look at this, I think you have 1 aluminum, 2 carbons, 3 hydrogens, and 23 oxygens. Wow, that's a lot. Okay? It's a lot. So how do we fix the situation? Yeah, we put the parentheses around here that says I've got 3 of these groups. Okay? Now, here's how you can check that any ionic formula is right. You always check that it's right. See if the oxidation numbers add up equal to 0. So, now remember, when you write the chemical formula itself, we don't put in the oxidation numbers. But you can check to make sure that you got that right. Oh, aluminum, that's still 3 plus. I got 3 acetates at -1. That's -3. I add those together, I get 0. So that's how you can always check that an ionic formula is right. Do those add up to equal to 0? Now, where it can get a little bit tricky is that, let's say you have something like this. Just for clarification. Let's say you have something like you have copper to sulfate. Okay? Now, as soon as you see ATE, where are you going to look? The monoatomics or the polyatomics? Miles.
ATE, polyatomic?
Polyatomics. Eights and ites are only polyatomics. Ides can be monoatomic or polyatomic. Most of the time, if it's an ide, odds are it's a monoatomic. Okay? It's rare that your ides are polyatomics. Some are, like hydroxide, okay, legitimately. But for the most part, ides are going to be the monoatomics. Not all of them, but a lot of them. Eights and ites, certainly, eights and ites only exist as polyatomics. So as soon as you see that ending of ATE, you're going to go, ooh, that's going to be a polyatomic. Okay? So here's the deal. You got copper at 2 plus, okay? And sulfate is going to be at 2 minus, okay? And there's certain ones you're just going to know because you're just going to use them so often. Sulfate is one of the most common ones. Sulfate's 2 minus, okay? So here's what you're tempted to do if you're going to do this cross step. You're tempted to take that 2 and move it here and take that 2 and move that there and go Cu2, SO4, 2. Do you think that's really what we need to do? Miles, you kind of were,
No.
Do you think that's what we need to do?
No.
No. How do you think we need to write it?
Take out the parentheses and the 2's.
Yeah, just right. So as if one is 2 plus and the other one is 2 minus, 3 plus, 3 minus, 1 plus 1. It's just going to bond in a 1-to-1 ratio, okay? You don't need the subscripts. So you just need to write this as CuSO4, okay? That's it. That's all you need to do. Just write it as CuSO4, okay? Don't transfer those 2's because they're already, it's in a 1-to-1 ratio because something is giving up 2 electrons, the other one is accepting 2 electrons. Okay. Now just keep that going. Let me hand out the lab. Okay. So what's going to happen, if you look on this lab, some of these I already have mixed up. So like these solutions, I've already got them mixed up. You don't have to prepare them. But all of these, notice, all I have is the names. You have to be able to write the formula. Now, there's one I'm going to give you because it's a molecular compound. So remember, there's generally, and as a broad classification, there's two types of bonds. There's ionic and there's covalent. If it's an ionic, it transfers electrons and you form charged particles. You form the cation, you form the anion. If it's a covalent bond, that just means that they share electrons. Covalent bonds primarily exist when you have non-metals that are bonding together, like sugars, for example, carbon, hydrogen, oxygen. Basically, covalent bonds exist because nothing has the capacity to take the electrons from something else. They have a very small difference in electronegativity, and they go, you know, you can't take electrons from me, I can't take electrons from you, but we need to form a bond, so hey, let's just share our electrons. So covalent bonds exist from the sharing of electrons. Ionic bonds exist from the transfer of electrons, and that's what makes the ions. If you don't transfer the ion or the electrons, you don't make the ions. So it's kind of like a catch-22. You want ions? Hey, you got to transfer electrons. So one of these that you're going to do is going to be methyl alcohol. So methyl alcohol has the formula of CH3OH. So if you were to build, I love these sets. If you were to build methyl alcohol, you're going to have one carbon. How many valence electrons does carbon have? Look, Etheridge. How many valence electrons does carbon have?
6, right? Did I get that number way off? Oh, 4.
4. Total of 6 electrons, but only 4 of them are valence electrons, right? Find carbon. Count over. 4. Boom. So what that means is that carbon has 4 electrons that it wants to bond with. So if you were to look at the Lewis dot structure of carbon, it has 4 valence electrons. So this is what makes carbon so unique. Carbon can form these big, long chains of carbon atoms. So like if you've ever paid attention when you buy gasoline, it has a certain octane rating, okay? Octane means that it's a chain of 8 carbons. So like an octopus has 8 legs, octane has 8 carbon atoms linked together, okay? That's what that oct means. So here's a single carbon atom. Now, and if you study organic chemistry, there's a whole way of naming different carbon atoms. So the methyl alcohol, so meth as a prefix means 1 carbon. If it's ethyl alcohol, that has 2 carbons. If it's propanol, pro means 3 carbons. So how we indicate the number of carbons is the prefix that it has with it. Okay? So methyl alcohol means that you have 1 carbon. So what happens is that this 1 carbon is going to bond with a hydrogen, okay? Then on the end of this, we're going to stick an oxygen with another hydrogen, okay? So this, if you were to look at a molecule of methyl alcohol, this is what it would look like. 1 carbon atom, 3 hydrogens, and then you have what's called a functional OH group on the end. So alcohol, all alcohols have an OH group on the end of them, okay? Now, so here's the deal. So this is going to be CH3OH. These are all made up of nonmetals. So what you'll see is that methyl alcohol and pure distilled water are the only ones that don't have ions in them. So what we're going to check is something called conductivity. Conductivity is basically a measure of how well a solution can allow electrical current to flow across the solution. if anything is going to allow electrical current to flow through it, on an atomic level, here's this atom. So if something's conductive, it allows these electrons to flow across it, okay? If it's a non-conductor, those electrons aren't free to move. So what I want you to see is that things that contain ions have these electrons on an atomic level that allow these electrons can move across. The electrons move across because they're free to move. Things that don't conduct electricity, they have electrons, but the electrons are bound up and they're not free to carry that electrical current. So at the end of the day, electrical current is movement of electrons. But again, Mother Nature is a lazy prima donna. Mother Nature is only going to make those electrons move because of potential difference. So when you turn on a light switch or you plug something into the wall, those electrons move because there's a potential. The electrons have to have a desire to move or they're not going to. So what you're going to do is that you're going to make a chart, okay? And on this chart, you're going to have the names of these things, okay? So for example, you're going to have distilled water, okay? Which means that's going to be the water that's going to come out of the squirt bottles. Make sure on this lab, what you're going to use to measure this conductivity is extremely sensitive. So you want to make sure that distilled water is your friend. And whatever you do, listen to me, whatever you do not take the cap off that distilled water bottle and put a pipette into that distilled water, because now you have contaminated that entire bottle. If you want to use some distilled water from a pipette, take that, pour that into a small beaker, and then pour that water out of that pipette. Never, ever, ever, ever put a pipette, anything into the distilled water containers. You've contaminated the entire thing, okay? So, you're going to have distilled water. You're going to have methyl alcohol. And you have the formula, okay? You already gave the formula for methyl alcohol. That's that CH3OH. And then you're going to measure the conductivity. Now, so conductivity is something we can measure. So let me explain how this is going to work. You're going to have the lab quest over there, and oddly enough, we have a conductivity probe. Okay? Cool, right? So this is something that we can measure. We don't have electronegativity probes because we can't measure electronegativity directly. But what we can measure is conductivity. So basically what happens is that this thing has this probe here. And what it does is that it measures how well this conducts electricity across the end of that probe. So, pretty simple. You're going to plug it into the LabQuest just like you've done a temperature probe or anything else before. Okay, y'all know the drill. Now, what you have to watch is that this has settings in what we call micro S. Okay, so and I tell you this on the lab. This has like 3 different settings. You want to make sure that it's set to the 0 to 20,000 micro S settings. Okay, that means it's a really, really sensitive setting. So what you're going to do is that you're going to have a test tube. Okay, make sure it's clean. When in doubt, wash it out. Take some distilled water, rinse it out, make sure it's completely clean. You're going to take this thing and you're going to fill it up with whatever that solution is. And you're only going to fill it about halfway. You don't want to fill it all the way up, and the reason being is that you're going to take this probe and you're going to put that down in here. Well, if you fill it all the way up, all you're going to do is splash everything out the end. So this is why you only want to fill it about halfway. Boom, put that in there, you'll immediately get a reading. So what you're going to need on this chart is the name, the formula, and the conductivity. Now, let's make sure everybody's cool. You're going to have, for example, calcium nitrate. You're going to go to your table, you're going to find the formula for calcium. Oh, Ca. Ca is in group 2. That has a charge of 2+. You're going to have nitrate. Nitrate is 1-. So I want to make sure everybody's cool. So you have calcium nitrate. Calcium is 2+, nitrate is 1-. So how are you going to write the formula for calcium nitrate? Emma.
Ca, parentheses, nitrate, parentheses 2.
spot on, absolutely perfect answer, okay? So like there's gonna be the formula for calcium nitrate. So you're gonna have to look on that chart, figure out those polyatomic ions. So when you get done, like let's say for example, you've done calcium nitrate, pour that out down the sink, then what you wanna do is rinse off the probe, because you don't wanna do the next one and carry that calcium nitrate onto the mixed solution. So you wanna rinse off this test tube, make sure that you get rid of all the calcium nitrates, just rinse it with distilled water, rinse off that probe in between, okay? You have to do that, or otherwise you're gonna cross-contaminate these solutions and then the lab is done, okay? So, that's what you wanna do. So then, you got some questions to answer. Now, you're gonna make a second chart, okay? So down here, I'm gonna have 3 powders: dextrose, silica, sodium chloride. Now, notice, let's look at the instructions. Down there at the bottom in section B, I tell you, place 10 milliliters of water in a 50 milliliter beaker, okay? Did I say 10.0 milliliters of water? No, I said it's 10, okay? Get about 10 milliliters, okay? Don't sit there and get a pipette and measure out exactly 10, okay? Take a graduated cylinder, get about 10 milliliters of water, pour it in, okay? That's all you have to do. Then you're going to take a small amount, visualize this, about half the size of a marble, and of dextrose. It's a white granular powder, sugar basically. So dextrose has the formula of C6H12O6, okay? It's a bunch of non-metals bound together. That's what sugar is. So you're going to put that, so here's your beaker. You put in about 10 milliliters of water. You're going to put just a tiny bit, about, not much, about the size of like half of a garden pea, of dextrose in there. You're going to take a stirring rod, give that a stir, make sure that you rinse that stirring rod off before you mix everything, because otherwise you're going to contaminate everything. You're going to get that poured up. You're going to pour that into a test tube. You're going to measure the conductivity of that. Then you're going to do the same thing with silica and then sodium chloride. Okay? That's what you got. So that's going to be your second data table. Okay? So you're going to have 2 distinct data tables. One for part 1 for section A, and the other one for section B. 2 completely separate data tables. Then, for section C, here's the third part of the lab. We're going to see if the concentration of a solution affects the conductivity. So the first thing you're going to do, we're going to look at 0.2 molar solutions, 0.1 molar solutions, and 0.05 molar solutions. Now, we're just kind of going to ballpark these. If we were really uptight about this, we would do this completely differently. But we're just going to get a ballpark idea. So the 0.2 molar solution, that's the one that you've done from section A. Okay, you're already going to have that number because that's the original solution. So then what you want to do to get a 0.1 molar solution, which is going to be half that, here's what you're going to do. Take your test tube, fill that about 1/4 full of a 0.2 molar solution. Then you're going to double the volume by adding water. So if you think about it, oh, I'm going to double the volume by adding water. That's going to reduce the concentration because it's going to become more dilute. So you're going to start with a 0.2, fill it about 1/4 of the way. Add water till it's about half full. Notice that this is so not a precise measurement, okay? This is just going to be something close. That's why I said we're going to go from 0.2 to 0.1. Notice I didn't say we're going from 0.200 to 0.100, okay? This is a ballpark, all right? Literally, this is just a ballpark. So by doubling the volume, you reduce the concentration by half because you're going to have the same number of particles, but you're going to double the amount of volume. So it would be like me taking all of you in this area, and then I'm going to spread you out into a room twice as big. The concentration of you guys would shrink by half because I would have the same number of kids, but I would have twice the size of the room, okay? Concentration would go down. You're going to measure that conductivity. Then, the third one, you can take the same thing. You're going to fill it about 1/8 of the way full, which is about like yay, okay? About 1/8 of the way. Then you're going to fill it up with water up to 1/2. Give that a stir, make sure it's mixed. Measure that conductivity, okay? So you're gonna measure the conductivity to 0.2 molar, a 0.1 molar, and then a 0.05 molar. And we're gonna see if diluting it affects the concentration of, or excuse me, if diluting that affects the conductivity of that solution, okay? So, let me give you a hint. So we've got about 50 minutes. Let me give you all a hint. Focus on getting the data first. Get your data tables, get those filled out, then worrying about answering the questions. Now, one of the things that you want to do is, on question number 6 on this back side, it says, would you predict a solution would conduct electricity if 3 drops of 0.2 molar potassium chloride were added to a test tube half full of methyl alcohol, okay? And explain your rationale. So you're going to sit there and go, okay, hey, what do I think is going to happen? So here's the deal. So you're going to have a test tube half full of methyl alcohol. You're going to go up to the solution that says potassium chloride. You're going to take a pipette and you're going to put in 3 drops of that methyl alcohol. So visualize this. This will make some more sense when you get there. So you have methyl alcohol, to which you are going to add an ionic solution. But you're not going to add very much of it. Okay? You're only going to add 3 drops to it. And so this is a prediction. Okay? There's no right or wrong answer. It's a prediction. But then you want to justify that. Okay? So it's the claim, evidence, reason. Your claim is, hey, is this thing going to conduct electricity or not? Why do you think it's going to conduct electricity, or why do you think it's not going to conduct electricity? And then you're actually going to test it to see if it does conduct electricity. Okay? So basically the idea being, the reason I put that in there is that you have 2 competing ideas. You have a molecular compound, a methyl alcohol, that doesn't have any ions in it. And then you're going to introduce some ions into it, and then you're going to say, will this conduct electricity or not? Okay? Maybe you think, maybe just a little bit. It isn't necessarily an all or none kind of thing. You might say, well, it will, but not very much. Or, there's not enough potassium chloride in there to do anything. Or you can sit there and go, those potassium, those ions are pretty conductive. If I have any in there at all, it's going to conduct. Okay, so that's what you want to think through. So then, section D, you're going to take tap water. This is the only time, listen to me. This is the only time in this entire lab you're going to use tap water. Okay, so you're going to open up the valve on the sink, you're going to take tap water, and you're going to test that conductivity. Everything else, it is absolutely vital that you use DI water. Okay? Absolutely vital you use DI water, because we want to introduce ions into this solution on our terms, okay? That's why we don't use DI water. So then you're going to take DI water and you're going to use that. Okay, are we ready? Ready to break? Let's go do science.